Yes? In the back too? All right. Hi, my name's Emmett Doerr. I work with Kosh and Monty and WinSE, and my presentation will be on code coverage. I want to give you guys a brief overview of what code coverage is, how we hope to have you guys using it in the future, and how you can use these technologies to improve your testing. Well, first, what is code coverage? Well, code coverage, generally speaking, is a process of finding areas of a program that are not exercised by a set of test cases. Using these tools, it will allow you to create additional test cases to increase the coverage of code through your testing. And it also allows you to determine some quantitative metrics on how successful your testing is and how effective your testing is and how much code your testing covers. It's a very structured testing technique. It actually uses several programming tools to determine how a program works based on its structure and logic. Now, if you contrast that to functional testing, where you're just running tests, this actually examines what the program's doing internally, and from that can make determinations on which test to run. So whereas traditional testing is black box testing, this is a white box test that allows you to look into the program, find out what your tests are covering, and from that information, make better determinations as to which tests you should run in the future. The goals, of course, is to make our testing better. Let's find new bugs that we wouldn't have uncovered with our old test cases. We can find out that if we take a code change, are we actually testing? Are we actually executing the code that we added or changed within our binary? Code coverage will tell us that. If we're not actually touching that new code within our binary, it'll tell us that so we can add new tests and determine that those new test cases, or that the new tests that we run, are actually touching that test code. A non-goal is not hitting 100% code coverage. Now, as I'll show you shortly, there's different metrics that you can find out as to what percentage of your functions are called, what percentage of the code within your functions are called. And the goal here is not to hit 100% coverage. The goal is to hit a substantial portion of which, determined by the test component owner, that you would deem effective in reaching and touching the most code, and just ensuring the best coverage of your binary. The reason why 100% coverage of your binary or of your component is hard to reach is, first of all, there's a lot of legacy code in Windows, and a lot of code that handles error cases that don't crop up very often. So we're never going to be able to hit all those cases. However, the goal is establishing a minimum percentage of coverage for each component and to strive towards reaching that. And that if we can hit a certain minimum percentage, if we can hit a certain, even just the delta of what changed in a service pack or what changed in a QFE, if we can establish that we've hit that delta through our testing, that we've covered the new error handling cases that we've added, that we've covered some risky new change that we put in some binary, then we've achieved, in my mind, a sufficient amount of coverage. So I'll give you an overview of how to do this. It starts with determining your features and determining your test cases. So any tester should begin with their regular test plan and the different test variations that they need to run. And what you will do is you will run these tests against a code coverage build. Now, we have special builds that are instrumented with certain binary information, binary instructions that will record exactly which code you're executing in Windows at any given time. So when you run your tests against a specialized build, you'll be able to find out and save to a database the exact information, the exact code that got executed when you ran your test. So to begin with, you want to take those builds, you want to install those builds, and you want to run your tests against those builds. Once you've run those tests against your builds, you can use tools to determine what was covered and what wasn't. Based on that info, you can write new tests, apply those to the same build, and review the information once again to determine if those holes were filled. I'll go a little deeper now and explain at a fundamental level how this technology works. It uses several tools that were developed in-house at Microsoft by some people at Microsoft Research. And the concept is very easy to understand. The implementation is a little messier, but at the lowest level, binaries within Windows are assembly instructions. They're code, machine code that executes against the processor. Now, when you compile your regular C code, you'll have if statements, you'll have branch statements, you'll have conditional statements, loops, and so on and so forth. However, when this gets converted to machine code, really at the most lowest level, it's just blocks and arcs. A block, the definition of that being a contiguous set of machine instructions that are executed without branching. An arc are the kind of virtual representations of branches that your code execution can take as it jumps between those blocks. So to take a very small concrete example, an if statement that evaluates a statement, and if true, executes the first block, if false, executes the second block. In that scenario, the first block would be a block of code, the second block would be a block of code, and all the combinations of branching that can take place, depending on the true or falseness of the statement that you're evaluating, would consist of the arcs. So what the code coverage service does on this instrumented build that we give you is it records the blocks and arcs that are hit by your program, or that are hit by your test cases. Then once those test cases are run, the data goes into a database. Now, to give you a better understanding of kind of how this concept works, I want to show you a program that's not used for code coverage. It's called VPEDIF, but what it's used to is to demonstrate and show the block and arc data within a binary. It's actually used to compare binaries, much as WinDiff is used to compare code changes. And so I can pull this up and demonstrate to you exactly how this works. So what I'm going to do is pull up two different versions of the same binary. The binary is going to be scuzzyport.sys, which is the storage port driver in Windows 2000 and Windows XP. And what I'm going to do is I'm going to pull the version of this binary from Service Pack 1 of Windows XP and the version of this binary from Service Pack 2 of Windows XP. And what this program will do, very similar to the code coverage tools, is indicate the blocks and arcs within this binary and what's changed. And the reasons for this will become clear, the reasons why I'm showing this to you. So this is looking at the binary level. This is not looking at the source code. And I'm going to skip all the header stuff and go straight to the procedures. And by analyzing the symbols, it has an understanding of where all the blocks are, where all the functions are within this binary. And by using some math, it goes in and it compares each function and the blocks and the arcs within those functions and determines what's different and what's the same. Now, if I stretch this out, I can show you here kind of what's happening within the binary, and hopefully this will kind of illuminate you as to what kind of data is this code coverage service saving. So say the scuzzyport dispatch power function, which is a power management function within the port driver, gets called. You can see here, this is the actual assembly instructions that would be executed by your machine if this function were called. And if you see these blocks here, these are the blocks of data that code coverage can record. The lines correspond to jump statements in this case, and these jumps indicate the arcs. So that not only does it record which instructions were executed, code coverage service also records the branching and the order in which those blocks are executed by recording this arc information. So if you look at this function in C, it's just a bunch of code execution, a bunch of if statements, a bunch of while statements. But this is how the processor sees it, and this is how the code coverage service operates. So by giving you that overview, it'll help you understand in the future how to analyze and interpret your data. We've gone through this already. Basic structure: run your test, view the information, analyze the data, plug test holes, run your new test. Ideally, the holes will be gone. From a practical standpoint, I wanted to have this slide to explain to you how to actually execute your test and save the data with code coverage. However, since these builds aren't yet available for Windows 2000 SP5, I can only show you against Windows XP. I don't have that demo prepared yet. But I want to give you a quick overview. Now, the important thing, the first thing to understand, is that you cannot run your test against a traditional build. You're going to be running it against a special build that we create. That special build is created with some added machine instructions that will actually allow us to save within memory, within both user mode and kernel mode memory, which blocks are executed and which arcs are taken. Now, once that data is saved, what we do as part of our process is to save these traces first to register them via a website. So for example, for every test case you have, say you're testing IIS, you might have a test case to serve out a static web page. You'd register that test case on a website so that you will be able to associate the data that you save via your test to one kind of overarching trace name that can be used to later pull up that data and analyze it. So you save that trace name to a website that might be IIS_serve static page, as the simplest example. You install the build, you run your test. A service that's running in user mode called covermon records the data that is executed during user mode. Likewise, a driver in kernel mode called coverage.sys records the data that's executed within kernel mode and all the drivers. So using some user mode tools that we will give to you, you can take this data from these services and save them to a trace name, to the same trace name that you executed on that website. You can save it to your local machine. Then you can run your other tests, save more trace data, run another test, save more trace data. Once this data has all been saved, you want to export it to the website so that you can actually view it. Now the reason for exporting it to the website is because Windows is a very, very interrelated operating system component, whereas when you're running your test against IIS, you're not just running code in IIS, you're running it against the entire Windows system. So by pulling all the information from all the trace names that all of the component testers within Windows have developed, we can come up with, in one database, a large overview of all the code that's been executed in Windows. So for example, by putting in this database, that somebody who runs storage tests against USB might be hitting functions within the kernel that might be of interest to a kernel tester. So in that case, if you take a change to a related binary like the kernel tester might not have any test cases of their own that actually touch that code, but the USB tester might. So by consolidating all this information in one place on a website where everybody can view it and everybody can access these trace names, they can determine, well, hey, we have another component under it that has a test that will actually touch a code change that we took in our component. And so this information can be very valuable when shared. So there's multiple ways of viewing this information from the website, or of viewing this coverage information once it's recorded. If you're here in Redmond, you can view it via the code coverage website, which I'll show you in a second. Also, you have to be here in Redmond to access this database. There's a tool called Sleuth that allows you more granular access to this data. It actually allows you to compare the information that's recorded in assembly and link that to the information in the code in C and C++. And by linking that information using this tool, you're able to compare what code got executed both in the assembly and in the C++. So that gives the tester a valuable piece of information in determining if their code changed or if the new code that was added to their binary was actually covered. Since they don't have Sleuth installed on this machine, I'll have to just show you the website. But this will give you a good idea of the kind of data that can become available. So this is the website. What I'm going to do is basically give a summary. So it knows who I am because I'm logged in. And it lists the binaries that I own as part of my testing, which are 29. And within those binaries, it gives me the percentage of coverage, which is 76%, which is actually pretty good. The components owned, 4 components encompass these binaries. And it actually tells me the binaries with no coverage in that area, which is actually interesting. It means I have one binary that's not touched at all. I should probably look into that. So I can click on my components and break this information down a little deeper. Okay, so my ownership encompasses storage drivers. So drivers IDE, drivers SCSI. You can see here that I have 81% coverage on the 7 binaries within IDE, 66% coverage in the drivers in SCSI, and likewise 85 for storage, 73 for tape. This table actually breaks it down into the number of traces that actually hit this component. Now you can see here that there's 181,000 traces that actually touch the binaries that are encompassed by the IDE component. And the reason for that is very clear. Any machine that has an IDE hard drive or an IDE CD-ROM drive in it that does any I/O to those IDE storage devices, any test that is executing on that machine will most likely pick up trace information from these components. And so that's actually very good for me in the sense that, say there's some special storage test that I'm not even aware of that touch my code. By looking at this information, I can actually determine that. Traces within my area, there's actually 2,000 of them. Traces registered, 27. Those are the ones that me personally I have registered. The number that have been run and the percentage of traces that have been run. Now let me break this down a little further. And this actually breaks down the different binaries within this component. So the important one here is a TAPI. It's actually interesting that we have 90% coverage here. So you get a very good overview. And if I dig even deeper, I can actually look at functions and within these binaries and find out what percentage of the code was actually hit within those functions. And so if I take a change to any one of those functions, I can look at this to see if those changes were actually executed. Yes?
How do you handle the same code is executed a couple of times? Maybe say the same code is executed say 20 times from the test case. So does it count it 20 times or does it be count only once?
It ORs the information for consecutive trace executions. Oh yes. The question is if you run multiple traces, if you run multiple tests at the same time, are you getting a...
The same blocks and apps or same piece of code is being executed again and again.
Okay.
So how do you deal with the code coverage?
So the question is, do we record how many times that we execute certain blocks and arcs, or do we just record the fact that we hit a block and arc? Is that your question? Okay, so the answer is we don't record the frequency at which we'll hit a certain piece of code. All we do is, in these traces, in these tests, is record whether or not that code was hit. They might be in the future recording the frequency, but the important thing is the assumption is made that a given test case will consistently hit the same piece of code. Now that's not always true, but that's an assumption that you can make and that you can actually determine by viewing the information. A separate question that I want to clarify also is that if you do consecutive runs of different traces against the same data, the database stores it cumulatively. So that if you run the same test again and you save that same information against the same trace name, that it'll be cumulative. So you can actually accumulate, even on multiple builds where the code is changing frequently, you can accumulate your total coverage so that if you rerun these tests, you're not losing your old trace information. Okay, so going back to the process for how you do this is that it starts by recording, or actually by creating traces on a website. Now a trace is merely, on this database, a representation of a test case. So in the case of IIS, a trace name could be IIS serve static web page. Okay, and so then that trace information, so that trace name is used as the tag for associating all of the blocks and arcs that were executed during your run of that test case. And so when you view the information on the website and you want to find out your percentage of coverage, the trace name, not the test name, is actually what's used to display the name. So for example, my storage testing, I have several tests that are run the same time but against different hardware variations. So rather than just putting the generic name of the test, my trace name encompasses both the hardware information, the hardware variation that the trace was run against, as well as the actual test case that was run against that hardware. So that way at a glance, when I look at the information, I can determine, oh, this code was executed when I ran this test case against this one hardware variation. And it's really up to the test owner on how you would like to name these traces. So you can make it as granular or as general and generic as you want. It's all what makes the information easy for you or for others to understand later when viewing this information. Are there any other questions I can?
How is this percentage of code coverage calculated? And is there any minimum criteria that if the code coverage is above this percentage, then it is good sign off.
So the minimum, the question was, how do you determine the minimum percentage of code coverage that you need to cover? That's on a component by component basis. And while management from above, the test managers have tried to say, yeah, everybody needs to have 60% coverage on their binaries. In reality, that's not always achievable. And so the metric that we've been sticking to is that each component owner should determine, based on what they know, since they know the component very well, each component owner should determine for themselves what is a good minimum level of coverage. I mean, we have legacy binaries where you could run all the tests we have in Windows and you'd only touch 5% of the code in those binaries. It's just that those binaries the code's not used very much anymore. So, you'll never be able to hit 100%. And it's not really relevant either because they're old legacy binaries, and if we're not touching the code, if nobody's touching the code, and we're not changing the code, it doesn't matter if we're not actually executing it. Yes?
Sorry, going back to this trace, can you show us an example of one trace?
Okay. Show an example of a trace. Let me see if I can pull one up in the website. They keep changing this website, so I go back. It's hard to find. All right. Traces. This trace information will be important to know later because when I get into the test prioritization, which I'll show you next. So here I have several ATAPI and driver traces that have been run against this component. And the naming convention I've used for Windows 2000 has been Win2K, ATAPI, which is the binary name, the class of the test, which is power management, and then we're hibernating the machine while the CD-ROM has been accessed. So while we're doing I/O to a CD-ROM drive, we'll hibernate the machine. And this trace data encompasses all the code that got executed while that test case was taking place. And see, I have similar traces for other binaries, Intel IDE, PCI IDE, which are the different bus binaries that are loaded depending on what IDE chipset you have in your system. Now, since these traces haven't been run against the latest builds, the data is kind of stale, so that means they have to be rerun. But I think if I click on one of these, it should show me some more detailed information. Okay, so what this is breaking down is for this trace, for this test that I ran, this lists every binary that actually got executed, that had code that was executed during the execution of this test case. And so there's binaries kind of all over the system. I mean, even stuff that's happening in the background gets picked up. It's not specific. So we're seeing stuff in CMD. I mean, CMD was probably loaded to execute a command line test. DFS, the system probably had some DFS links created. The interesting thing is it spans the entire system. So while I'm running my test, there might be interactions with other components that just from a high-level black box perspective, I'm not aware of. This captures that information. Okay. Let's save all the questions for the end because I'm going to move on and I might be able to answer some of the questions in the next part of my presentation. So. Already answered this. Do I need 100% coverage? Not necessarily. It all depends on the nature of your binary, and that's a decision for the component owner to make. Next question, which holes should I plug? Now here in sustained engineering, what we're really doing is we're fixing bugs, okay? We're changing code within our binaries to solve a specific business problem, to solve a specific bug within Windows, okay? So our strategy in Windows sustained engineering has been to really get coverage on the delta, on the code that we're actually changing. Now, there's binaries in Windows that we haven't changed in the service pack. Is it really necessary that we get coverage on all those binaries? Well, in effect, yes, because if we change it in the future, it's important to know which tests actually touch that code in the first place, so that if we change that code, we'll know what tests to run. But relative to which holes you should plug, if you have a test hole that affects a function that is never really executed, or has not been ever changed within a service pack, it may not be necessary to actually plug that hole. It's up to the test component owner. Okay. Now here's where it gets interesting, where the value of these tools really kind of come to bear is in test prioritization. So now that we have this data in the database that lists which blocks and which arcs were executed for which test case, I mean, that's all well and good. We can look at that data and we can find out what blocks got hit or what percentage of blocks got hit. But that's all kind of like, whatever, you know? That just tells us what got executed and what didn't. What's really interesting about this data once it's in the database is you can actually use it to prioritize your test cases. And we have a tool to do that called select test. Now, from a high level, what select test does is it takes a code change. It'll take a new binary that you have a code change in. So that could be a QFE binary, that could be a private that you compiled on your own desktop, it could be anything. And then what it does is it looks and compares that against a previous version of that binary that the trace information within the database was executed against. It uses some of the same tools I showed you before in that VPE diff tool. Now, once it has that differential information, it goes into the database of all the trace information, and it determines, of all those traces, which of the test cases are most likely to execute the binary, or to execute those code changes, rather. So, in the simplest example of a code change, where you have a single block, and you're just changing one line of code within that block, what select test, which is the test prioritization tool, will do is it will go in, it will notice that that is the only block that got changed, go into the database, and find out every test case that hits that block, and create a report of that. And so you can look, of all the tests you've executed, or even of all the tests that anybody's executed in Windows, you can find out, oh, these are all the tests that I need to run to actually touch that code block. The idea being there, if you run those tests first, then you're more likely to hit that code, and if you're more likely to hit that code, you're more likely to verify that the expected result of your test case is, in fact, the right one. You can't really find a bug in a new code change if you're not actually executing the code, is an assumption that's made. In a more complex case, where you're actually adding large pieces of new code, it gets even smarter. And it says, okay, well, I executed this block and this block, and we inserted 10 new blocks within there. And so based on that information, based on the test that executed the blocks around it, it can make an assumption, it can deduce that these traces are more likely to execute that new code than, say, code that only hit the block after. These tools become very valuable, and we're actually starting to use this as part of our regular check-in process on our war meetings to determine that if basically how risky is a change. So, for example, if we run this tool and we find that it affects every trace in Windows, obviously that's a risky change, and maybe we should do a little more testing before we execute it, or before we check it into the build. If it doesn't affect any traces, maybe it's a very low-risk change, and we can check it into the build much faster. I'm going to give you a quick demo of this, and hopefully this will make things more clear. Okay. So what I'm going to do is I'm going to show you the same binaries I took before, and what I'm going to do is I'm going to compare that against Windows XP Service Pack 1 and all the traces that were executed against that. So the database, in addition to containing information based on the traces that were executed, it also has information on the blocks that are within each binary, the static information that doesn't change, so that when I give it a new private, it doesn't need the old binary in order to determine which blocks were changed. It can look to the database for that information because it's all stored there. No, it's in test. And so what I'm actually feeding to this tool is the Service Pack 2 version of SCSI and what I'm going to compare it against is Windows XP Service Pack 1. And there have been a lot of changes in this binary since Service Pack 1, so it might take a while, but in fact what I can do is I can pull up a block filter that will allow me to limit the analysis to prioritization data based on only the blocks that I specify. So say I want to find out what test cases I should run if I'm changing this function. What I can do is I can go through all the changes within this binary. It'll take a minute to compute. And I can limit the execution to those code changes. So I'm going to unselect all because there's 1,800 blocks impacted. And I know we changed a lot of this code, so let me check a bunch of these blocks. And that'll make things a little more clean. Okay? And then I've set a filter, and those are the only blocks I would like to view. I can run this right now. So for larger binaries, this can take a long time because you're actually comparing against millions and millions of rows in a database. Oh, okay. Well, I don't know if this will necessarily work, but let me try a different database. No, I don't think this is going to work. Sorry about that, guys. But if this were to work, it would generate a report. First of all, explaining from a high level which blocks were changed in that binary that you fed the prioritization tool. And based on that information, it would go through and it would list blocks of tests. So the idea is never one trace. It's never the case where one trace will completely encompass the code changes within one binary. So what it will do is it will give you the groups of traces. It'll say, the drivers IDE hibernate, drivers IDE this, drivers IDE that. And it'll give me a list of generally 10 to 15 test cases, traces within this database that will give me the best percentage of coverage against these new code changes. So usually, for most changes, it'll spit out a group of about 8 to 10 test cases that will cover about 90% of that diff. Sometimes it's lower, sometimes it's higher. But the prioritization data is extremely valuable and extremely useful because, if nothing else, it tells you what traces, what test cases are most likely to touch that code change. It makes the tester, it makes their lives easier by knowing which tests to run first. And it also boosts the quality of our product because by prioritizing, we can hopefully find bugs sooner. Okay. And an important thing to note is that sometimes other people's traces will yield better coverage on our own binary than our own. That often happens. Because as Windows, as it is just every component has multiple dependencies, and every test case is always running tons of code within the operating system in order to accomplish anything. So it's very interesting viewing this data and finding out that, hey, a kernel test is actually, touching my port driver code better than, all the test cases I've created. Sometimes it happens, and it's a very good and interesting way of combining the test coverage that everybody within Windows has developed. How to plug your test hole? Well, multiple ways. You can write a new test, you can draft a new test case, or you can even run somebody else's test, which is sometimes the easiest and the best way to do it. The end result is better testing. So in conclusion, it's just a tool. You cannot rely exclusively on this information for making determinations on which tests you should run and which you shouldn't. However, it can really help you make some better educated decisions as to which tests you would like to run, or how risky a code change may be, or even, are your tests good at all? Do you need to add new tests, or do you have a pretty good set of test cases already? If used correctly, it can yield some powerful results and be used to test Windows better. And with that, I'd like to answer any questions for you that you may have. Yes?
So what I understand is that the amount of code that we touch while executing the question is how significant is this number to us? I mean, given the fact that my code coverage is 100%, I can never say that my test cases are tested the code completely or very well.
Mm-hmm.
It might happen that the test case, I mean, the scenario in which the test case were executed, it might have touched that code and it might have worked fine for that particular scenario.
Mm-hmm.
But in some other scenarios, say 10 other scenarios, it might have not worked.
Mm-hmm.
So, like, how significant is this information to us when you say that your code coverage is 100%? You are still not sure whether your code, I mean, the testing has been the better testing or the.
Right. The question was, how can we be sure, how valuable is this information if we have 100% coverage on our binary? Yes, if you have 100% coverage on your binary, you know probably every line of code is getting executed. However, you're saying is that it might not be encompassing certain scenarios that will actually lead to bugs, even if you do have 100% coverage. And that is very correct. But remember, just the percentage of coverage on your binary is only the first part of the equation. Is that by getting this data, the important thing from a sustained engineering perspective is finding out for a new code change, which of these traces will affect that code change. And that right there can help narrow down the testing field from, millions of test cases to run to, only a few dozen. But you are right. There are certain components where this technology will be by and large useless because of the way those components work. It will only give you the information that, yes, this code got executed. It won't necessarily give you the context which that code was executed such that it will lead to a bug. So this is used to complement and supplement your existing testing. It still takes a smart tester to use this information. For other binaries, though, for other cases, it's like if we have a new error handling case that we want to determine if, in drivers, it's especially important in dealing with errors correctly and handling those correctly. We can find out if these error handling cases actually got executed. So we can actually tell if these errors are happening. You can't actually test the error handling code if you're not seeing errors. So it varies by component. Your mileage may vary, but if used effectively, it can be used to definitely help and improve your tests. And it's best that you speak with your WinSE component owner to find out what was their mileage in using this. Some components it works really well, others it doesn't. Best way is to try it out and see how valuable the data is to you. Anybody else? Well, great. Thank you very much.